Hello everyone. So please let me introduce our work, Tensor Decomposition via Core Tensor Networks. I'm Jianfu Zhang from Recon AIP. So before introducing our work, please let me demonstrate the assumptions. Traditional tensor decomposition methods always treat every image individually without considering any correlations. However, different input tensors may share some common structures. Learning tensor decomposition individually will ignore these correlations and be more time-consuming when the number of input tensors is large. So when the dataset contains a large amount of data, existing methods cannot give out results fast and accurately. Proved by other methods like basis methods and deep learning methods, leveraging the correlated information might be helpful for convergence and accurate representations. Traditional tensor decomposition methods find a low-rank approximation of the observed signal, following the popular tensor decomposition models such as CP, tensor train, or tensor ring. These methods search for the best low-rank decomposition by optimizing algorithms like gradient descent or alternating least square with random initializations. The optimization problem is non-convex. Yield initialization may lead to a spurious local minimum and slow convergence. The most powerful advantage for DNN is the scalability and generalizability of different data. DNN can learn models on training data and memorize the data patterns, then infer the results with fast or even without retraining on new data. With pre-trained DNN models, we can infer the initialization for tensor decompositions with prior knowledge, which can help us decompose the tensors fast and accurately. In this paper, we apply tensor decomposition to unsupervised tensor reconstruction, which consists of two different tasks: tensor decompletion and tensor denoising. Some of the entries for the input tensors are missing or observed with random noise. We aim to complete or denoise a bunch of data concurrently. Here we call the decomposed small tensors as core tensors. We can learn the core tensors with gradient descent algorithm by calculating the partial derivatives of the core tensors on the objective function and update the core tensors. The optimizing process for each iteration can be depicted by this equation and this algorithm. We run gradient descent with maximum 10,000 iterations, or if the difference of the loss function between two adjacent iterations are close enough. Now let me introduce the proposed coordinate tensor network. We designed a simple neural network to learn the core tensors based on the input tensor called core tensor networks, which can build global network models for all the input tensors and learn the core tensors based on the network parameters. Here we use multilayer perceptron to learn a function representation for the kth core tensor with network parameter theta. We call this as the main cotensor. Please note that for all the input tensors, the network parameters theta are shared. We replace the original cotensor representation with some of the main cotensors and bias cotensors, which are not shared among all the input tensors. Similarly, the original gradient descent algorithm, we designed gradient descent for the core tensor networks. The details are shown in this algorithm. With CTN, we can initialize the core tensors with random projections of the input tensors. the values of the core tensors can be related to the original values of the input tensor because we can compute the core tensors with the inverse core tensors and the core tensors itself. Hence, this can improve the learning speeds to converge for tensor decomposition with this random projection initialization. On the other hand, the main core tensors share the same model parameters for all the input tensors, which means we can combine different tensor decomposition processes together for better performance and robust results. To further improve the convergence speeds of core tensor network, we utilize meta-learning to pre-train the network with auxiliary training input tensors. Meta-learning methods learn models applicable to different tasks. Here, we decompose the learning process for main core tensors and the bias core tensors into two different tasks. For each iteration, we sample a batch of tensors from the training set. We initialize the bias core tensors and optimize the bias core tensors for gamma steps with the current main core tensors computed with the network parameters. Then we update the parameters for the main core tensors based on the learned bias core tensors. The learning process for the test input tensors are the same with the previous algorithm. The goal of meta-learning for core tensor network is to pre-train the model parameters for the main core tensors with the training set and fine-tune the model to the test set. Here is an illustration of this process. If the gamma here goes large, the bias core tensors for each training batch are more precise, which means the model parameters theta are also closer to the global optima of different input tensors. But larger gamma means more time to train the network. Here we find a balanced choice for gamma empirically and improve the convergence speed for the proposed core tensor networks. Here are the experimental results. We test the core tensor network on image completion tasks. The color image resolution is 256 and the input tensors are reshaped to 9 order tensors. We compared gradient descent alternatingly square, core tensor networks, which is called CTN here, and the core tensor network with meta-learning, which is called TCTN here. All the experiments are run on GPU. We can see that CTN and TCTN perform better with much less time. This is the plot of loss function of the numbers of iterations during the optimizing process for convergence analysis. We can see that CTN converges about 4 times faster compared with gradient descent, while TCTN sharply reduced the loss function with just a few iterations. We also analyze the gamma, which is the hyperparameter for TCTN, to determine how many steps to learn the bias cotensor before updating the model parameters for the main cotensors. As we can see, when gamma goes larger, RSE performance becomes better for TCTN, while when gamma is large enough, RSE remains consistent and does not improve. So here we choose gamma equals 20. And these are the comparisons between CTN and TCTN and different state-of-the-art methods. On the left are the results for image completion, while on the right are the results for image denoising. CTN and TCTN perform better than all the algorithms listed. On the middle part of this slide, we show the saliency map of the first layer of CTN. The saliency is defined similarly to GradCam, which is a popular visualization method for deep learning. We can see that saliency map shows some patterns of the image. Different core tensors, different tasks have different patterns. Here we list the possible future works of the proposed core tensor network. The first one is to replace the fully connected network into convolutional neural networks. Convolutional neural networks cost less model parameters, which means that we can build deeper networks for better performance and also preserve the local structures of the images. We did try CNN in our experiments, but we failed to get a compatible result in this work. The second one is to analyze the patterns of the core tensors and use these informations to other tasks like classification. The final one is to theoretically analyze the core tensors to prove the convergence improvements theoretically. So that's all. Thanks for listening. If you have any questions, please refer to the paper and feel free to contact me via email. Thank you.
Thank you, Jianfu, for the talk, and so now for the Q&A session. There are I asked so you can ignore the first question because actually you answered it in the talk just after I asked it. So you can go to the second one, and if other have questions, please write them in the chat.
So, okay, thank you. So the question is, how does the size on the dataset affect the quality of the outputs on the test set? In particular, what would happen if you run your algorithm on a dataset with only one image? So that's a very good question. We did some experiments on this question, and we find that for different settings, like image completion with 10% kept or 30%, the experiment results are different. So if you choose to keep the 10% of the image and you ran image completion, maybe you only need 10 images to run the core tensor network. Say if you have more than 10 images, like 30 or 100, the performance does not improve too much. So if you choose the setting like you keep 30% of the images and you run the image completion, maybe you need less images. That depends on the percentage of the image completion. So I hope this can answer this question.
Yeah, absolutely. And actually, I had another question. I was about to write it, but I didn't finish it, which was about how. So, in your experiment, do you reshape the input images into higher order tensor, or do you keep the same shape as the original image, or do you reshape them into a higher order tensor?
I just reshaped it into a higher order tensor, and so
and how does
because so we can continue.
Sorry, and so I was wondering, how does the algorithm scale with the order of the tensors? Like, is it more efficient, computationally intensive when you start to get to higher and higher and higher order tensors, or does it scale very well with the order of the tensor?
I remember that if we choose to reshape the tensors like lower order, like seven order tensor instead of 9 order tensor, the performance is worse. I think so. So maybe the order tensor, the order of the tensor is higher, the performance is better.
Perfect. Okay, thank you very much for your answers and for the talk.